Per, thanks for introduction. As Per said, I come from Croatia. My name is Katja, and in my free time I mostly work with hardware because I really like it. I also have some of the boards with me, and more over here, and the big one that has a lot of cables plugged in. And I would bring more, but it's really tough to bring them for airport security because they don't like it, and they ask questions. So when I was coming here, I can guarantee that you can bring 3 boards, and if you say you are doing password cracking on them, they will let you go because they don't want to know why they do that. So why do we do energy efficient bcrypt cracking? I mean, you could ask yourself those questions like, bcrypt is really slow, it's sequential, it's really designed to be resistant to those hardware. And it's easily to ask yourself, why bother optimizing? I mean, why would you even do that? But we have those platforms which actually behave differently when you implement bcrypt on them, because they are able to use some peculiarities of bcrypt to actually achieve performance much bigger than you could do on a CPU or GPU, which are like, they do common stuff. So the outline of this talk is the following. I will give a short introduction of bcrypt, then we'll go through different implementations of bcrypt. There will be power consumption data, short demo, and future work and conclusions. So let's start with bcrypt. It's based on a blowfish block cipher. It uses expensive key setup and user cost setting. It's important to know that although we use cost 5, at systems today you should use 10 or 12 because 5 is insecure. It's there for historical reasons. And what else is important for bcrypt are pseudo-random memory accesses and memory usage of a bit over 4 kilobytes, which is pretty large. So if you already know everything about bcrypt, he's blowfish, so you can admire the wonders of nature. And bcrypt uses blowfish encryption based on this Feistel network. It receives 64-bit input, divided into 2 halves, and those halves are fed into the network. P boxes, so these P1 to P18 are actually P box. There we have passwords, user password stored. And the most important thing on this slide is this. Actually the F function, because it uses 4 32-bit loads from those S boxes, and these are pseudo-random, which makes it not possible to predict them and prefetch them. So this whole thing is used in expand key function, where blowfish encryption it returns 2 values, left and right, and it changes the state 2 by 2. And state is defined by the contents of S box, 4 kilobyte large, and P box, 72 byte large. The whole bcrypt algorithm uses what we just saw and encrypts it with the magic value 64 times with SCB mode. Another thing that is really important to notice is this loop. It's repeated 2 to the power of cost times, which means that user chooses how many times it will be executed. So the user chosen parameter determines computation time. And this is how the hash looks like. So it consists of mode, cost, salt, and actual hash. So let's see how does it look like when you implement it on hardware. First architecture is Parallella with Epiphany multi-core chip. So Epiphany has 16 or 64 32-bit RISC cores, which operate on up to 1 GHz. What is important to notice is this. It consumes only 2 watts, and it's really only 2 watts for both 16 and 64 core. Another important features are really high amount of local memory per core and really high amount of register, which is untypical in today's CPUs, and FPU, which can be switched to integer mode. There are also some cons. to this architecture, and that's actually the latency of FPU, which is 4 cycles, and the fact that it can issue only integer instructions. But with a large number of registers and 32 kilobytes of local memory per core, these cons can be easily overcome. This is how the chip looks like. So there are 64 cores, network on chip, and basically all the stuff that I already mentioned. So let's start with implementation. The first thing was to actually just implement it in C and see how it performs. And the result was 820 cracks per second, which, well, it made me happy because it worked. But when I compare it to like high-end CPUs, then it was like, oh, it's not so good. Well, the first optimization was actually compiler optimization with directive to just move the code to local memory, because some portions of code were put in shared memory. So moving into local memory and actually enabled instructions to be fetched in 1 clock cycle, and resulted with improvement. Then that was all it was possible to do using only compiler-generated code. And as I mentioned earlier, there is FPU in integer mode, and compiler couldn't use it. It couldn't just see, oh, this instruction could be issued on FPU, and did it. So it was necessary to write it in assembly. What you see here behind is one of the tries of scheduling instructions. And, well, it was really bad one. After it, few times it locked up the board, and later it was slower than compiler-generated code. So I had to try it again, and sometimes see a sunrise, and finally get to 976 cracks per second. Well, lot of work for 40 cracks per second on cost 5, so for cost 10 or 12, fairly significant. But if we have 2 bcrypt instances per core, then there is enough instruction level parallelism so that FPU can actually be fully utilized and used, so that actually there are instructions that are issued on the same cycle, so 2 instructions, one on arithmetic unit and one on FPU. So with all of this, we again started only with C, just to see what compiler can do. And well, it's slower than optimized code for 1 instance. But as we saw earlier, there are 64 registers, and pbox has 18 values, so 36 values for both instances, and that can easily fit into 64 registers, and compiler is smart enough to do it. So with that code, it's almost 1000 cracks per second. And again, assembly. This time, it really paid off. In the end, 1207 cracks per second compared to 820 that was on the beginning. This is just a relative speed up of different implementations. And it is really important to notice that optimized assembly implementation for 2 bcrypt instances is much faster. Mostly because we actually have enough instructions to use the underlying hardware platform. And this is how it looks like in assembly. You don't have to read it. The goal is to see that blue is instance 1, red is instance 2. As we can see here, there is something called I-add, which is integer add, issued on FPU. And it has latency of 4 cycles, so we fill it with instance 2 to actually get the result after it. So one of those instructions is issued at the same time as the blue one. And here's how it's actually used in the whole bcrypt algorithm. In summary, we have 2 bcrypt instances per core, optimized in assembly, and integrated in John the Ripper. This is performance for 16 cores and for 64 cores. So this is how the board looks like. I just showed it earlier, it's here with me. And these are the numbers. So it achieves around 600 cracks per second per watt. And on the bigger one, it's 4,800 cracks per second, or 2,400 cracks per second per watt. Also, what's important to see, it's really scalable. It's almost exactly 4 times faster on 4 times bigger board, and it's also really easy to just port it to a bigger board. You change this directive and recompile. And this is actually this was used during the development. This is prototype of Parallella, and the actual board came on the market a bit later. So now we come to the FPGA implementations, and well, we'll have a short break because, like, as we saw with assembly, there are a lot of details, but with FPGAs, it's much more technical and much more detailed. And actually, at the one point, I had draft of slides which are almost unclear to me. So if you have, like, during this time, if you have questions, feel free to ask, because it might be not so clear. This is the architecture of Zinc board. So it's hybrid platform. ARM Cortex with FPGA logic. And the first implementation I'm going to show you is actually not optimal at all, and it's actually a really bad one. But it's here on these slides to show what happens if you have a wrong approach to FPGA implementation. I mean, on CPU or any general purpose hardware, you can't really go that bad if you miss a bit. But on FPGA, it's really easy to get things working not so good. So in this implementation, what we have is basically this. Green stuff is on FPGA, and blue is ARM processor, which cannot be changed. So these communicate through DMA and AXI interface. So ARM sends data into this PROM, and then bcrypt reads it. So it's called shared because it's shared among all these bcrypt instances and between processor. And it is block RAM that's actually on FPGA. So this was like really bad, almost embarrassingly bad. But well, let's say it worked. I didn't want to try high performance on any higher cost because I don't know actually how many numbers after the decimal point John can show, and I was afraid it would be 0. So what? Frequency here is 100 megahertz. So with some modifications, it was possible to achieve 300 cracks per second, which is just a bit more decent. And more modifications. So if we waste a bit of VRAM and speed up implementations, it's possible to achieve this speed. These numbers aren't really important. They're just to show what happened with most straightforward approach, with just the one that just worked. Also, another thing is that bcrypt isn't complex. I mean, it's small when it fits, when it goes into FPGA, and utilization here is insane. And it's mostly because of this. So each of these cores have to go through another module to actually copy data that it needs for computation. And this is the reason for high utilization, and the fact that pbox was stored into distributed RAM, which also affected these numbers significantly. So it was necessary to do complete redesign. Completely avoid DMA and avoid sharing any resources that are not necessary to be shared. And this is how it looks like. Again, green part is on FPGA, blue part is processor. This time, Exibus is the only thing used to transfer the data, and data is stored in corresponding VRAMs. So there is no unnecessary copying or any other unnecessary computation. So what determines the number of parallel instances is available VRAM. And memory layout and how the VRAM is used actually affects that number. So we can see here the simplest approach. Put S boxes into one VRAM. One VRAM has 4 kilobytes, so perfect fit for those S boxes. And put all the other data needed for computation in another one. So this data here is around 160 bytes. And this VRAM has 4 kilobytes, so it's waste, most basically. With another approach, it's possible to have 5 VRAMs in one module. So 4 of these just hold S boxes, like here. And the 5th one holds other data for all of these 4 different instances. What we gain here is actually 5 VRAMs instead of here it would be 8 for the same instance count. Another thing is, you may ask yourself, okay, so this is half empty, not half empty, that's almost empty. And why don't you just fill in as much as it can fit? Well, the reason why we don't do it is because each of those VRAMs has 2 ports for read and write. So in one clock cycle, I can read only 2 values out of this VRAM. And I need, as we saw earlier at bcrypt, I need pbox values on every round of blowfish encryption, so I need it in every second cycle. So that's the reason why this isn't filled until it's full, actually. So what happened with this memory layout? Only most costly loop, the one that runs to the power of cost times, was implemented in FPGA. So some computation was done on host, and some was on FPGA, and those were interleaved. Clock frequency dropped because of higher number of instances, which caused routing overhead and delays. So we have two layouts. 2 VRAMs, where we can fit 70 instances because there are 140 VRAMs on Zinc 7020 device. We run it at 2 cycles per blowfish round, and performance is 2162 cracks per second, which is just a bit less than 3 times better from the not so good approach I showed before. It's also it's really important to notice that it's limited by communication overhead, because here we transfer 4 kilobytes for each instance. So it's 4 times 70 kilobytes of data with really low clock, so it takes time. With another approach, we have 5 VRAMs, and we can fit 112 instances. However, it's unstable. ZBoard has some hardware defects, so it reboots. There is a third memory layout, which is also, well, looks like a waste, but actually it's not. See here, we store S boxes, 2 in each VRAM. So every instance has 2 VRAMs for 4 S boxes. This means that it's possible to fetch all 4 needed values in a single clock cycle. So we wasted half of those VRAMs, but this time one blowfish round can be calculated in a single clock cycle because we have everything that we need in that single clock cycle. Also, we have another VRAM holding all the other data needed for computation. And you'll see later, this can actually hold initial S-box values, but we'll come to that. So if we implement whole algorithm in FPGA, part of communication overhead is actually removed because this time we need to spend less data. At the beginning we spent 4 kilobytes and 160 bytes of other data, and then we return only the hash, and hash is fairly small. So with this approach, performance is much larger. As you can see, it's 3,700 cracks per second, but it's still limited still limited by communication overhead, but this time much less. With this approach, it's possible to fit 56 instances. So here we had 112 and 2 cycles per Broffish round. Here we have 56 and 1 cycle. So at the end, these are the same, because we do twice less instances, but twice faster. And if we transfer initial S-box values, then this is the performance, 4,500 cracks per second. However, it's still limited by communication overhead. So what we tried was to avoid it, but using those unused parts of VRAM to actually store initial values for S-box 0 and 1 and 2 and 3. Because these do not change, these are digits of number pi. Unfortunately, unstable and Z-board reboots. So we saw that all the designs look nice and promising. They actually do not work on real hardware, so we modified it. You don't really have to read all of this. It's important to notice that there was a problem with voltage drop, and there was a problem with insufficient decoupling. So to solve this, we added the wire, which brings more current, so the drop voltage goes up, and we added capacitors, so that the decoupling is reduced. And nicely, 112 instances do work. However, Z-board reboots because of overheating. So we added a fan, and at the end, the design works. It's stable and reliable. So these are results. Severely limited by communication overhead, but if we look at the higher cost speed, where communication overhead becomes negligible, then it's 64 cracks per second for cost 12. And if we derive cost 5 performance without overhead, it's actually 8,100 cracks per second. So it's 10 times faster than the lousy implementation from the beginning. However, 56 instances with hardware modifications, where we wanted to see if how will it behave when there is indeed no communication overhead, is still unstable, still doesn't work, and Z-board just reboots. However, we have a bigger zinc board, and if we emulate this on a bigger zinc board, then it's performed on 7,000 cracks per second, and we can see for cost 12, these are nearly the same. So indeed, those two designs perform the same. This is the look of the board, with a huge heatsink, lots of wires, capacitors and stuff. And this is actually the design that's stable and which works. So we have also this C706 board with zinc 7045, which is roughly 4 times bigger than the zinc chip that can be found on Z-board. So we saw, let's see what we have to do there. What we did was just to port the best Z-board design to bigger FPGA. Unfortunately, this board comes with almost the same hardware defects, so it's not possible to achieve expected performance. And we have theoretical core count of 436 cores, or if we use that approach with 10 VRAMs, then 216. The highest stable that we were able to achieve is 196, and really nice performance of 12,000 cracks per second on cost 5. So let's see how we're doing with some other architecture that aren't FPGAs and embedded systems. This is Xeon Phi from Intel with 60 cores and really nice color and vector units. These vector units have 16 32-bit gather loads, which are really promising for bcrypt, because then we can load all values we need from S boxes in a single clock cycle. And each core supports 4 hardware threads. So first we use John the Ripper with existing builds, so OpenMP and OpenCL. These are a bit, so OpenMP is a bit higher with 6,200 cracks per second. And yes, no, it's not. I mean, it's we were expecting it to be, but as you can see on performance, it's actually not. I mean, I'm not sure what happens during those gather loads. No, I don't. So with using VPU unit, actually the performance drops and it should be much higher. So all the other things that we tried didn't improve the performance. So the guess is just slow. I mean, we don't know the architectural details of gather loads, and they just don't perform good enough. And the last architecture that we tried to use was Haswell, also from Intel, with AVX2 instructions. And bcrypt code was written by Steve Thomas. Thank you, Steve. And with 8 bcrypt instances per thread with this performance. However, these 8 threads use over 64 kilobytes, like data cache size is much lower. So we tried to modify the layout to stay in cache. And these are the results that we got. Although we are still in the cache, and there should be no additional latencies, and we should be able to exploit those gather loads, performance is much less than existing non-AVX2 code. So what seems to us is that these gather loads are just slow, and only thing that we can do is wait for Intel to do something new. So let's take a look at power consumption. This is a huge table for CPU. Actually not there, so to read it right now, but later when slides will go online. What's important to see that range of performance for from 1,200 cracks per second until like nearly 17,000, and efficiency of those platforms from 35 to 80 roughly. For GPU is a bit different. Performance, the lowest is 800 and it goes up to nearly 8,500 cracks per second. And efficiency is even lower than on CPUs. And then, if we look at energy efficient platforms, we see that these performance numbers are comparable to what we saw here and here. But efficiency is much higher. Like even for the Epiphany 16, which has the lowest efficiency, it's still much higher than any of those. And let's see some bar charts. So if we compare Epiphany directly to x86 CPUs, we can see, another thing that's important here. Epiphany 16 and T7200 are fabricated in the same technology, 65 nanometers. And this is important because fabrication technology affects energy consumption directly. So Epiphany 64 and i7 are nearly the same. This is 28, this is 32. So when we compare these platforms that should have the same efficiency, same or near the same energy consumptions based on lithography, we see the performance is nearly the same, while energy efficiency is much higher for energy efficient platforms. So if we compare various selected platforms, we see, okay, this zinc is the highest, but all the others are nearly on the somewhere near each other, and we see again energy efficiency of efficient platforms is much higher. Another important thing to look at is how much these boards cost. So we took the system price and chip price or device price and compared it to each other. So the metrics here are cracks per second per dollar. So we can see that energy efficient platforms also are really can be compared to all the others that we use, while their prices are significantly lower than prices of some other these other devices. So here is important to note these prices, all of these, are prices and introduction, because it was the most fair to use the prices of brand new hardware, because the older hardware prices dropped the most, so it would be unfair comparison. And another important comparison is to look at system price and only device price. So for energy efficient platforms, it's really easy. System price is price of the board, chip or device price is price of the chip. So, and one notice, like these 99, that was intended price and introduction, but currently board is more expensive. It's $119. For other platforms, for CPUs, we used, for system price, we used device price plus $300, because you cannot just plug CPU and like, it's not plug and play. It needs motherboard, DRAM, and heating and power supply unit. So we estimated those on $300 and added the device prices. And as we can see, actually Zinc 7020 performs the best. So it's device price, device cracks per second per dollar price is performance is the highest. Earlier I mentioned a couple of times that actually there is a significant communication overhead on FPGA implementations. And to see how platforms compare to each other when there is no communication overhead, we did this. So basically this formula here, what it does, it counts number of blowfish encryptions. We have 512 plus 9 here, 2 to the power of cost, which is 12 and fine, times 1024 number times of number of blowfish encryptions here and here, and we actually divide those two to get the ratio, and then multiply it with performance we measured for cost 12. So we have these numbers that are measured numbers. We have these estimates that are computed using this formula, and then we have measured performance, measured performance for cost 5. So we can see that the Epiphany is completely optimal. The same holds true for CPUs, this GPU, and Xeon Phi. However, Zinc devices have much higher estimate than their actual measured performance because of communication overhead. And more formulas. This is the theoretical analysis of what could be achieved. So here we have number of ports that device can use to read data, read SBox and PBox data. We have number of blowfish encryptions. We have 16 blowfish rounds, and 16 is actually how many rounds there are in a single blowfish encryptions. And we have number of reads. So if we put numbers into this formula, we come up with this. So these are theoretical estimates. Number of reads differs from some of those platforms because for Epiphany architecture, there were enough registers to preload P boxes. So we didn't have to read that one. So there were only 4 reads for S boxes. And on other platforms, we actually need to read S boxes values and P box value. So we have in total 5 reads. So as you can see, actually FPGA's theoretical estimates is really close to theoretical performance for cost 5. However, on all the other architectures, things aren't so bright. For Epiphany, we can see that estimate is roughly 4 times bigger, and our assumption is it's because architecture is computation constrained, and I mean, we don't know enough details to be able to fully explain it. Another interesting thing is that those two i7 CPUs should perform nearly the same, but i7-4770 performs much better. Why? It's also assumption that this device is somewhat computationally constrained and has some internal latencies we aren't aware of. And also, these two use actually the John the Ripper built for CPU, so it wasn't optimized for specific architecture. So if we really would take any of these and then do all optimizations we can, these numbers would be closer to the estimates. There is also related work on this topic by Frederick Wimmer and Ralph Zimmerman called Speed and Area Optimized Password Search of bcrypt on FPGAs. What they achieved is bcrypt running on Z-board at 80 MHz, 40 instances running in parallel, and these are their numbers. For cost 5, they have really nice performance without, I guess, without much communication overhead. But as you can see, from cost 12 performance, our current design outperforms there. So there is also a short demo. So this one is for Epiphany board I have here. And there is also really big, oops, everything is live, really big Xilinx Z706 board. And so I'll start demos. Of course, hashes are failed. So on Z-board, Zing device, and Parallella. So as you can see, this one is already finished, 4 seconds. This one is still struggling. And this one is the slowest one. It's Epiphany 16 with the lowest performance. So we can see here that it took 90 seconds for the Z-board and only 4 seconds for the bigger Zing board. And now the Parallella is done. But here I used the 4 times shorter word list, no, 3 times shorter, because otherwise this demo on Parallella board would take about almost 2 minutes, so it was a bit too long. I want to go back slides. So future work on Parallella and Epiphany device, as you could see from performance numbers and or theoretical analysis, it's completely optimal implementations. And another thing that we can do is use both Epiphany and Zing device at once, because Parallella board do have both of these. Another interesting property of this architecture is the fact that there are links for integrating up to 64 chips here. So with scalability of current implementations, and hopefully Adapteva will produce these big boards, theoretical performance is 300,000 cracks per second. With FPGAs, we have still room for optimizations on Zing devices. We should improve clock rate and reduce communication overhead. And also, we have this ZTEX Bitcoin miner, which is multi-FPGA board with disconnected fan now. And it has 4 Spartan 6 FPGAs. And the goal is actually it was produced for Bitcoin miner, but the goal is to use this hardware to actually do bcrypt cracking. And some conclusions. So we saw that many core RISC architectures and FPGA boards can actually exploit some things that are particular to bcrypt and achieve comparable performance and much better energy efficiency. So what's the actual consequence of this? So as you saw, like on those boards, they either have a heatsink or the bigger board has a small fan. Those are actually they don't heat much. So it's actually, this enables higher density because we can put much more boards in a tiny case and they will be able to actually survive in those conditions and to work properly. So there we have more chips per board and more boards per system, which means for these low-cost platforms, attacker has much more cracking power for the same cost. And we saw we never use ASICs, and we still improved energy efficiency by a factor of 45 and plus. So I think, yeah, it would be interesting what ASICs would do, actually. So I would like also to thank some people, Sayanatan Data, who actually implemented bcrypt on GPU, Steve Thomas, who implemented AVX2 code, Parallella project for providing the boards, Google Summer of Code because that's how it all started, Xilinx for donating the big ZC706, and my university because actually it's not my board, they borrowed it. So, thank you. So, are there any questions? Yeah, okay, great, thanks. Do we have another microphone for the questions? Yes.
Did you try it with DSPs at all? Did you try it with DSPs?
Yeah, we tried to use DSP slices, but they also had latency of 1 cycle, so in total it didn't improve the actual implementation. Oh, okay, no, I misunderstood the question. I'm sorry. I thought you so Zinc FPGAs has DSP slices on it. No, but we didn't try like DSP processors. No.
So I saw in one of your slides you were talking about cracks per second per watt, and it looked like the Parallella 64 was really, kicking Intel's ass for about exactly the same cracking rate per chip. Was it a correct interpretation to say that the Epiphany 64 was like 500 times more power efficient than the Intel?
No, it's actually 45. I mean,
but it was like there was the one with the really low bar on the i7. Yeah.
Okay,
that one.
So it's 51 and 2,400, so around 45, 46 times.
Okay.
Yeah, but it's significant. Yeah, another question.
Did you try to lower the frequency for FPGA because the energy consumption usually rises over linearly? So maybe at a lower clock rate, it would.
Okay, so thank you for the question. it's a good one. So you see this idle to load delta is around 1 watt. So if we would lower clock frequency, it would severely impact performance and communication overhead would be higher. And we'd go, I mean, even if it's twice lower still, it won't go much below this 1 watt. So, yeah, I mean, the only time when we actually tried it was for unstable designs. So to see if it will become stable with lower clock frequency, but that didn't happen. So guess is that it doesn't affect power consumption that significantly.
So as you've pointed out, bcrypt requires the 4 kilobytes of memory, which is, you know, for FPGA is quite a bit of memory. So what do you think the biggest consumer of power in the computation is? Is it the actual math, you know, doing the addition, the rotation, the XOR, that sort of thing? Or is most of the energy consumption in the actual memory accesses and storing the values in memory? And then I have a follow-up question.
Okay, yeah, I think it's actually the memory, because as you can see earlier, we changed the design to actually store initial values and then copy it, and that caused instability. So it certainly draws more power than before, or some other causes another problems. But yeah, I think it's limited by Pyram.
So then my follow-up question is, you know, 4 kilobytes of memory is extremely difficult to handle even in like an ASIC design. It's just a lot of memory. And if that's the biggest power consumer, do you really think that an ASIC would be that much more power efficient if you had to implement 4 kilobytes of memory, where if that's probably the biggest consumer of power?
Well, I think I mean, it's really hard to say because it really depends on type of facing and what you actually do with them. But I still think, I mean, there you have a freedom to implement it on a gate level, and you have much more control over the stuff. So I think it would still be better. Thank you.
Bueller.